Great to be here. So I'm Niels Bultink from Qblox, and I'm here to talk about bridging the gaps between high-performance classical and quantum computing. So what are we doing with Qblox? We are entirely focused on the central part of the stack, where what we call the control stack, where we translate abstract notions of gates and measurements into the electrical signals that are driving the quantum chips, and then getting back electrical signals from the chips and translating them back to the user. So that's what we do. And we do this in a way that we create very scalable control solutions that are useful for, that are ready for useful quantum computing. So let's define useful quantum computing. What do I mean here? So at this moment, we currently find ourselves, all of you in this room, on this two-dimensional map, with on the bottom axis this number of qubits, and on the vertical axis the error rate. Depending on the team you're in, you're a bit more on the larger qubit count, or you're a bit more on the lower error side. Pick your favorite. But the point is that there are two ways to get to applications, roughly. The first one is to get to this noisy intermediate scale era with some useful applications and perhaps even very worthwhile. But there's a second path, and that's towards the fault-tolerant era. The first needing a little bit of scaling and a lot of noise reduction, and the second needing a lot of scaling and in the end also a lot of noise reduction. So there's a lot to do, but let's talk today about the three challenges in the control stack for scaling on zich, for running NISQ algorithms, and for fault-tolerant quantum computing. So let's start with scalable tuning. Important in scaling up devices and reducing errors in the system is three parts of the control stack. The first one in having a very modular and integrated control stack. The second is the computational power that is embedded in the system in a distributed fast sequencer cores. And the third part is in the analog excellence that creates pure signals. So on this modular integrated architecture, we here show the cluster device as we now install it with many customers today, where the system consists of 4 different flavors of modules, 2 on the control side and 2 on the readout side with various frequency ranges. And in short, this allows you to build control systems with just in one box everything you need for 20 transmons or 20 quantum dots. So in this case, an example for this, what can all fit in there with this 20 transmons. So we're roughly at a density of 100 qubits per meter. So already today this allows for building stacks with hundreds of qubits without much overhead in space and overhead in complexity, as everything is embedded in the same system. So how to control all the channels in this system in a meaningful way? We need very good sequencer cores to offer the right orchestration of all of these channels. And what these sequencer cores' main task is to schedule the pulses and the gates throughout the time and throughout all the channels in the system. And where our architecture pushes the envelope is in the fact that there are these Turing-complete processors, many of them running at the same time, that can do logical operations like adding or jumping, if statements, and that also connect to a bunch of pulse shaping methods that can all happen at the nanosecond time scale. And the combination of these two aspects is very powerful for tuning up quantum devices. And I'll give you one example to show how this improves an experiment. So in this case, this is a typical prototype or a typical tuning protocol where we are tuning up a pulse shape of one pulse, in this case a 2-qubit gate, and we have 2 parameters that we want to vary. And we're mapping out the overall process fidelity as a function of these parameters. So usually these type of experiments are very time-consuming, in this case about 90 minutes. And there are 2 ways we dramatically speed up these type of experiments. So the first is in this making the control stack very autonomous. So the pulse variations, as well as all the data analysis and storage, is done completely autonomous, reducing the time to just 22 minutes. Then if we add the layer of qubit reset, fast qubit reset, this experiment even goes down to 13 seconds. So this is just one example how these flexible sequencer cores can really mean a big difference in tuning up quantum devices. And because it's distributed, you can run these experiments in parallel at all of your qubit pairs at the same time. That's what we call scalable tuning. So a third aspect of scalable tuning is the fact, what are the noise levels in the system and how can we reduce them? So key in many experiments is 1/f noise and drift. Noise to improve the gate fidelity, drift in keeping the gate fidelity constant as well as possible. And there we've also pushed the envelope by multiple orders of magnitude in both of these aspects. So that is for scaling up the systems in general. But now I want to particularly more talk about the noisy intermediate scaling challenge and highlight the challenges there. So I'll now be zooming in a bit more at the top end of the stack, the interaction between computational resources and the stack itself. So if you take any NISQ type of algorithm, they basically always look roughly the same. There is a quantum circuit you need to execute that has a bunch of parameters in it. All the gates are parameterized in a way. And after executing the circuit, you analyze the result, let it go into an optimizer, and spit back new parameters for the optimizer. And the whole trick is in doing this iterative process of executing this quantum circuit, doing your classical computation as fast as possible. Because any time that you're losing in this classical part is actually dead time for your quantum processor, and you want to use it as much as possible. So how do we perform at the moment? We can do this iterative type of procedures in just a fifth of a second, roughly, by employing these fancy qubit reset tricks, as well as some variable tuning of the parameters. And this is the entire loop of the optimizer, as well as executing the circuit, as well as the communication. So this is great news, but at the same time, I also don't want to pat myself too much on the back, because there's still a lot of room for improvement. And that is because the actual quantum circuit, the bare circuit is just 2 microseconds. We average it for 2,000 times, so the raw compute time is just 3.5 milliseconds, and we're taking 0.2. So there's actually a lot of room for improvement, and that is mainly in this classical part. So in this case, 15% of the loss is going in the communication between the control stack and the host computational resource, and 83% is lost in optimizing and in doing the recompilation in the computational research itself. So solving these bottlenecks is really about placing your quantum system close to high-performance compute resources, and that's what we're going to do. So the first thing is really embedding it close to powerful resources, and the second is in creating better communication between HPCs and quantum circuits. So thirdly, let's talk about quantum error correction, where we will have to addressing the bottom end of the stack, really the interaction between the control stack and the quantum device. So, first of all, what is quantum error correction roughly in general? What does it look like? You have a quantum chip at the bottom, and in this quantum chip, errors are going on. And the task of quantum error correction is to infer these errors via so-called parity measurements, and then use all of these parity measurements combined to understand what the underlying errors are. And this is in an abstract sense what quantum error correction is. But why is it so difficult? That is in the fact that the qubit coherence times, if you're assuming quantum dots or superconducting circuits, is just 100 microseconds. And we need to do all this error decoding and correction tasks in a small fraction of this. So that's what the big challenge is about. So if we break it up, what does a parity measurement look like? The bare circuit itself is actually just about 1 to 2 microseconds. So most of this time is taken by the quantum circuits as well as the measurement. And then there's just a fraction of a few hundred nanoseconds available to communicate our measurement results and make them central and then decode. So in practice, what this looks like is as follows. We have all these readout modules in parallel that get measurement results from parity measurements, and they upload their measurement results to a backplane. Then this backplane channels all these measurement outcomes to a central point where the decoder lies. That is where magic happens, real magic, because this is really a core academic field in trying to get these decoders up and running. And after processing these decoders, the corrections get fed back down to our quantum circuit. So what do we offer as Qblox? We're very good at channeling all these measurement results to a central decoder part. What others in our community are very good at is developing these decoders. So we work together with a lot of decoder experts, both academic and corporate, to offer them access to the best experiments in the world. To the experiments, on the other hand, we offer the best possible decoders that our other partners have. So that's how we operate. So in conclusion, as a company, we are working with many partners with different quantum circuits. We have key projects in scalability for quantum error correction as well as NISQ algorithms. And we're always looking for more partnerships, for more people, so feel very welcome. Thank you.